Okay, today we'll discuss how to derive gravitational potential energy. Right, I'm going to have to give you some background. So, generally for gravitational potential energy, we have to define some place as a zero reference. Right, just like when we use MGH, we normally set the lowest possible level to be 0 GP. Right, then we calculate H from there. Right, from their reference zero. Okay, likewise in this case for gravitation in terms of planets, right? We tend to define infinity as zero gravitational potential energy because that's the best reference that we can have for planets, right? So if at infinity I have a small mass m, right? Let's say this m over here, right? The m at infinity will have 0 GP, right? If I bring this mass closer to the Earth, all right, at constant velocity, right? Constant velocity is important so that I do not change the kinetic energy of the mass, right? So if I have constant velocity, all the work done by external force right here, all right, will actually go towards changing the gravitational potential energy. Okay, so how to maintain constant velocity? The external force must be always equal in magnitude and opposite in direction to the gravitational force. All right, I'd like you to remember that this one is not Newton's third law. All right, because Newton's third law is not acting on the same body m. Alright, so F external and Fg are not related by Newton's third law. This is a hypothetical case whereby I force the F external to always be equal to the Fg so that there's no acceleration on mass m, so that it doesn't change the velocity, so that the k don't change, right? So now we want to try and figure out what is the work done by external force when I shift a body m from infinity, which is this position, right, all the way to a position here, which is a distance r away from the center of the Earth. Right, so work done by external force will be given by integrate from infinity to r f external dr. Right, generally work done you should understand by now is always area under the FR graph. Right, so technically it's this area. Right, this actually this graph obviously extends to infinity lah, but I can't draw infinity lah. So infinity is somewhere to the end of the axis. Right, but this is the FR graph. Right, so by right it should be area under FR graph, and this is the F external force, right? So this line here represents F external force, right? But F external, right, is always equal and opposite to Fg as mentioned earlier. So I can write F external as negative Fg, but I know that Fg is negative gmm over r squared. Alright, so this negative here and this negative here will eventually cancel. Therefore, you get a positive gmm over r squared over here. Right, and obviously you're going from infinity to point r. That's why you integrate from infinity to point r. Right? When you do the integration, you realize that gmm are constants. So r to the power of minus 2, you plus 1, then you divide it by minus 2 plus 1. That's how you do integration. Right? Then you will get something like minus gmm over r. Right? This minus sign comes from the bottom here, because this minus 1. Right? And obviously the r become power minus 1 over here, right, which means there's 1 over r, right, and you integrate from infinity to r because I'm going from infinity to r, right, so when you sub r inside, you get this, minus gmm over r, and you sub infinity, you get minus gmm over infinity, which actually is 0 because anything divided by infinity is 0, so this part is already 0, your final answer will be just minus gmm over r, right, but work done by external force is also change in potential energy in this case, gravitational potential energy, because remember that we made sure the velocity was constant, so there's no other change in energy, right? So all the work done by external force goes towards changing gravitational potential energy only, and gravitational potential energy is final minus initial, but remember what is initial? 0, because we set that to be 0, right? This ui, which is 0, and therefore my final gravitational potential energy at a distance r away from the Earth is actually minus gmm over r. Right, if I want to find potential, right, which I told you in class is a proxy to measure gravitational potential energy, right, then I'll just divide by the energy, which is ur divided by small m, which is this mass, right, and that will give me the gravitational potential for the Earth, right? So this gravitational potential for the Earth, or you can say this is phi m, capital M, alright? This is gravitational potential energy of the small mass and the Earth as a system together, alright? Right, now I'll try and link this with one of the generic formulas you have learned in class. Alright, remember from here, right, from here, this part over here, we learned that delta U is actually integral of, which delta U is work done by external force, right, in this case, because K don't change. Right, so delta U is equal integral of infinity to R minus Fg dr, right? I'm going to do some horrible maths here, so if you're a maths teacher, please ignore this, right? I use this equation. I'm going to change this delta U into du, right? I'm going to move the dr over here, and then I'll form this equation, which is du over dr equal minus Fg, right? Where this is the gravitational force, right? So this is the gravitational force, and you realize that you get a formula Fg equal minus du dr, right? So what this means is very simple. Here it means that in this case, right, if I want to look at Fg, right, on the graph, it will look like that, right? But it will be the integral of this thing, right? So Fg is like that, right? So what this means is that if I look at the force R graph for this case, right, the negative of the integral of Fg dr, which is this area under graph, which is obviously negative, is actually the times a minus sign. So times a minus sign will give you the change in gravitational potential energy, right? So that's the meaning of it. The area under graph here, of course you must times the minus sign, give you gravitational potential energy, which you know is this dr already, right? Then if I want to swap the equation around like that, what I'll get is if I look at the energy against R graph, alright, the gradient of the energy against R graph will be the negative of the force. Alright, so that's why I get this formula, which is the general formula that relates force to energy, right? Fg equal minus du dr, right? So this is the gradient of the, again I repeat, gradient of the energy distance graph, negative is the force, right? And that's how you get this formula over here, right? So you can see that UR is minus GMM over R. If you differentiate this, alright, you get R to the power of minus 1, you bring down, become positive. That's how come the negative sign here disappear, right? Then it become R squared below. So you get GMM over R squared positive. But remember that there's a negative sign here. So you have to add in a negative sign here, right? So that's why the FG is fulfills the whole circle, right? That's what you get. That's why your Fg is minus GMM over R squared. If you look at in front, right, you see Fg is GMM over R squared. Alright, so this full circle, right, to show you everything together, right? So why did I show you this part 5 is because small g is a proxy for gravitational force. So if I want to find small g from this value, I can just take the gravitational force of planet Earth, in this case capital M, divided by small m. I'll left with minus gm over R squared. And if you look at this and this, you realize the relationship between this and this is actually this, which is the same as this one, right? This is what? Fg equal minus du dr, which is unsurprising because the relationship between this is just divided by m, and the relationship between this is also just divided by m. So if these two, which is potential energy and force, are related by this formula, I would expect that their proxies, which is this one and this one, will be related by the same formula, right? Okay, so these are two general formulas. All right, you don't have to worry too much about the integration here, as mentioned in class. H2 don't test integration, but this is just for understanding and completing your picture of how we derive gravitational potential energy, as well as how come force is related to minus du dr. It actually comes from this work done formula here. Alright, it starts here. Okay, with that